I'll be talking about how very strong transition took place from traditional world to the quantum world. The understanding that we used to have in the framework of Newtonian mechanics, and how things translated to a new state of world, what we call commonly call as quantum world. Throughout the the human history, our understanding of the natural world has evolved. It has evolved from the realm of classical mechanics. You may also call it as classical physics, to the groundbreaking concepts of quantum mechanics. This kind of transition that goes from classical to the quantum realm, it marks a significant shift in our perception of reality, and really has led to profound revolution in science. So I have classified this small presentation into these six categories: classical physics, then I'll talk about quantum revolution, then quantum world, quantum weirdness, some applications, and I'll try to conclude this philosophical discussion on these topics. So, before the advent of quantum mechanics in the early 20th century, the scientific world view was dominated by classical physics. It was developed by the personalities like Isaac Newton, James Maxwell, and so many great philosophers in the realm of mathematics, in the realm of physics, and some chemical sciences. And classical physics could successfully describe the motion of microscopic objects, and it could provide a comprehensive understanding of mechanics, electromagnetism, and thermodynamics. And to be precise, classical physics was deterministic, assuming that exact position and the momentum of the particle could be precisely predicted and measured. And then then there was a beginning of quantum revolution, and this quantum revolution started in early 20th century, and there were many contributors to this mathematical philosophy, like Max Planck, Albert Einstein, Neil Bohr, Erwin Schrödinger, uh, and so more and more people who were involved in the quantum revolution, and their ideas revolutionized our understanding of the subatomic world. They proposed a revolutionary theory of quantum mechanics, uh, which uh, which challenged the deterministic approach that was predicted by the classical physics. So this quantum mechanics introduced the concept of duality, the dual nature of the particles, like electrons, protons, neutrons, or atom as a whole. Then this quantum revolution, it certainly was a step that was taking us to a new realm, to a new domain. Uh, that new domain is what we call as the quantum world. So this quantum mechanics describes the behavior of matter and energy at atomic and subatomic levels. It is governed by Schrodinger's wave equation, which provides a probabilistic description of particles' behavior rather than definite trajectories that we have in classical physics. In classical physics, we have trajectories where a particle will move from one point to another point. It has it has definite trajectories. Its position, its momentum, it can be calculated simultaneously, and it could be its future could be completely predicted. But here in quantum world, we don't have that precise, the accurate prediction. We have probabilities. We here deal with the probabilities. The outcomes here in this case are probabilities of finding the particle in different states. Then there is, there's a lot of weirdness in quantum mechanics, and such statements were given by the great physicist Richard Feynman, said that quantum mechanics, quantum physics is very weird when we try to translate it into some kind of physicality. And this this quantum mechanics introduced several counter-initiative and puzzling phenomena. What it did, it proposed uh, it proposed the things like superposition, where particles can exist in multiple states simultaneously, and this is what a common sense, for a common sense, it's very weird, and making a situation where we have a particle, and unless and until we will measure it where it is, it's everywhere at the same point of time. And this is totally against the intuition of human mind. And and then there is another important parameter here in quantum weirdness. We call it quantum entanglement. In case of entanglement, we have two states of particles, and these particles become correlated to each other, irrespective of the distance. That means if some kind of action is being executed, one particle, if there is uh, entanglement between the two particles, even if the other particle is at another corner of the universe, uh, there will be a response from the other state, uh, from the other state on which another particle or is being placed in a very very hypothetical way. So, to be precise here, it is like that where the entanglement is something where the particles become correlated regardless of their distance apart. And then comes the applications of the quantum field, the quantum mechanics. It has led to numerous technological advancements, such as transistors, lasers, nuclear energy, and so on. And there are quantum technologies coming in action, like we have quantum computing and quantum cryptography. The quantum computing and quantum cryptography, they hold a promise of of revolutionizing computing and communications. And there can be challenges and unanswered questions, and uh, despite its incredible success, the quantum mechanics is very successful, and it may have more success in future when it will be translated into a full-fledged quantum computer. Uh, uh, but still, there are a number of issues where this theory, the quantum theory, it's incapable of giving the precise results of most of the problems. So so it certainly has incredible success, but there are a number of unresolved problems for which there is no window that we can see through quantum mechanics. And in conclusion, I would like to say that the transition from the traditional world of classical physics to the quantum world of quantum mechanics, it marks a fundamental paradigm shift in our understanding of the universe. The non-deterministic nature of the quantum realm has not only expanded our scientific knowledge, but also opened it has also opened new avenues for technological innovations and exploration. And quantum mechanics continues to inspire our curiosity as scientists to strive to uncover the mysteries of the common world. Thank you.